Sussex AI seminar. I'm going to share about my research on the human augmentation in robotic surgery. So I think you already know me a little bit from the introduction. Let me shortly introduce myself again. So I was born and grown up in China. And after my bachelor study, I went to Nanyang Technological University for my master and PhD study in the group of Prof. Su Jifei. And after that, I went to Imperial College, work with Prof. Etienne Burdent, and also working on EU project, collaborate with Freiburg University and Sorbonne University. And in about 2 years ago, I joined Sussex as a lecturer. My research is about human augmentation in robotic surgery. So we all know that robotic surgery is increasingly used in hospitals. And compared to the conventional open surgery, the minimally invasive surgery brings many benefits to the patients. It has less blood loss, also small scars, faster recovery. Many of the current robotic systems in robotic surgery are using teleoperation systems. In this kind of systems, the surgeon sitting behind a master console, remote control the slave robot at the patient side. So this figure is showing the famous Da Vinci system. We can see from that the surgeon is operating using hand controllers and the vision feedbacks. And the at the patient side, there are robotic system interact with the patient. But the standard cooperation still need not only one surgeons, need many collaboration between the surgeon and their assistants. But the collaboration introduced some teamwork errors. Actually, there's a growing evidence showing that the communication in the operation room among the team members is a common issue. The WHO guideline for safer surgery has stated that the communication issues in the operation room are the primary point of vulnerability for patient safety and efficiency. And about 70% of the adverse events in the operation room are due to the communication errors. But we know that there are so many surgical scenarios require close cooperation between surgeon and their assistant. So next slide, I would like to show you some examples of the surgical task involve more than 2 instruments. So in the first case, the assistant need to control the laparoscopic camera to help the surgeon to adjust the viewpoint, and the surgeon is operating the main surgical tools. And in the second case, it's about the flexible endoscopic surgery. The endoscopists need to navigate and load the instrument to provide the surgeon's view of the operation area, and also navigate to the proper operation target area. In the third case, the assistant need to control the suction tool to suction the blood or air to keep the surgeon a clear view while the surgeon perform cutting or suturing. And in the fourth cases is for the laparoscopic radical prostatectomy, that the assistant need to elevate prostate base to great tension for the posterior blade and neck dissection of the main surgeon. And the last figure is showing the case of laparoscopic hysterectomy, that the assistant need to grasp and lift the tissue while the surgeon perform cutting using monopolar scissors and forceps. So all the cases are illustrating that in no matter open surgery or robotic surgery, we need close collaboration between the surgeon and their assistant. Then in that case, how do we solve this communication issue in the operation room? One possible solution is to augment surgeon's capability to control multiple tools at the same time. So it's kind of like a science fiction of Dr. Octopus, where the one surgeon can control multiple instruments all by themselves. But we are human, we just have two hands. Then whether we can add a third hand to surgeon, we know that in the teleoperation system, the surgeon interact with the remote system through hand interfaces or the other human-machine interfaces. Then in that case, whether it's possible we develop some hand-free interfaces, enable the surgeon to use their other body parts to control the third tool and work together with their hands to perform multiple tool manipulations. So in this presentation, I'll merely talk about my work on developing the hand-free interfaces. We have developed a 4-degree freedom foot interface to enable the surgeon to control assisting tools like laparoscopic camera or endoscope, flexible endoscope. And we also develop a robotic system which enable one surgeon to control 3 instruments in flexible endoscopic surgery. And we also show our EX vivo test with a toxin tissue. And last, I will also share some human studies we have conducted in the virtual reality. So let's start the story of augmentation with review of the body interfaces. There are already some body interfaces existed in robotic surgery to control the tools like camera. There are many options to select the control source of this third hand. So we can use the head movement. We can also use finger movement when the finger is not used in the operation. There are also systems use the voice command. But when we choose the design source and develop the interface, we need to consider some requirements. So first, the selected hand-free source should not affect the mean operation of hand and also visual feedback and communication in the operation room. Because the mean surgeons need to focus on the mean operation, they still need to communicate with the other team members, and the eyes need to focus on the mean operation area. So we don't want the third hand control affect the mean hand operation. And secondly, this input signal should be easy to detect with less noise. And due to the limited workspace in the operation room, so we hope the interface have a very compact structure, don't occupy too much space. And also, we will use this interface to control a third tool, manipulation tool or camera. And these tools normally need to move in the space in multiple degree freedom. In our case, we want to control the flexible endoscope. It needs to move in the space in 4 degree freedom. So we should allow the hand-free interface to control more than 4 degree freedoms. And we also consider the operator in the design. So we want to provide intuitive mapping for the surgeon to operate the tool. So the surgeon don't need to spend too much time to learn this interface. And because many surgeries also take a very long time, we also don't want to introduce too much physical fatigue or mental effort to the surgeon. So in our design, we have choose foot control because in robotic surgery, the surgeon is in a sitting posture and their lower limbs are free to move in the space. So this provides a task-independent control source. So then we go to the design stage of the foot interface. So we first do some analysis of foot movements. So we select 4 degree freedom foot gestures based on human biomechanics. So there are 2 degree freedom translations in the horizontal plane and Fourier rotations and pinch rotations. So we didn't choose lift up and down because it takes too much human effort. They need to lift the whole leg. To collect all those foot gestures, we have located 8 feedback and sensing modules around the foot. So each module is a serial connected spring and a force sensor. So in the motion range of the springs, so the module is in elastic mode. So the human user's foot can move in this workspace. And also the spring will provide some elastic feedback to tell the user where's their foot. And when the spring reach the compression state, this will reach the boundary of the motion, so it transfers to isometric mode. So the human user's foot cannot move anymore, but the load cell will still record the force. So this design avoids the ceiling effect of the position and make the system input only depends on the foot capability of the user. So based on this idea, we have designed the structure of the interface. There are several options of the structure. We can use serial structure, parallel structure. So here we choose a hybrid structure, combine both parallel and serial mechanism to avoid the coupling of motions and also guarantee a compact structure. So the final prototype is similar as the other simple foot pedal in the operation room. So the interface mainly includes the base, which is fixing on the ground, and the mobile frame, which can move inside the base in 3-degree freedom, forming a parallel structure within the base. And the pedal is serial connected with the mobile frame, and it can rotate in the pinch degree freedom. In the initial design, we located the compression spring outside of the base to provide user the positioning assistance. But we found that this kind of structure will have two extreme yaw rotations to make the pedal uncontrollable. So to avoid these two singularity positions, we locate the spring outside of the base. Instead of inside the base, we locate the spring outside of the base. So this provides a singularity-free configuration with a minimum elastic energy position in the middle, so which is also defined as a home position. So once the operator finishes the operation and release their foot, and the pedal will automatically go back to this home position and also provide them a resting position for the user. So this slide has shown the 3D drawing and the final prototype of the interface. So interface enable 4-degree freedom movement, and the movements are not limited to single Cartesian movement, but any combinations of those movements, like diagonal directions. So it's quite like natural movement of human user. And we also consider different foot size of user. So there's an adjustable foot fixture, so you can adjust based on the different foot sizes. The next step, we are thinking about how do we compute the motor commands and then map to the motion of the robot. So we first use the traditional analytical way to build a kinematics model and the statics model based on the structure of the foot interface. But later we found that so this kind of calculation and modeling doesn't consider the individual user. It doesn't depend on the structure of the interface. So if some users' motion pattern is quite different from the others, it may introduce much error. In that case, we want to check first what's the human foot motion pattern. So we conducted a pilot experiment study with 10 participants using the proposed interface. So we asked them to move to 8 single Cartesian directions and 12 diagonal directions. And we want to check, so these two figures in the slides is showing the foot path error, which is defined by the deviation from the real trajectory and the desired trajectory. So we can see from the figure that in most of the cases, the deviation is large between subjects, but is relatively small within a single subject among same trials of this subject, among different trials of the same subjects, especially in the single Cartesian directions. So this motivates us to further develop a user-specific mapping method. So we have defined a quick calibration procedure. So we ask participants to move in the single Cartesian directions, and then we collect the data of these 8 single Cartesian directions, and we use the independent component analysis for this calibration data to extract a 4x8 mapping matrix T. And this matrix will be used to extract output control command for this specific user, so they can follow their own motion pattern in this case. And based on that, we also further develop a foot interface to control the grasping degree freedom of a surgical tool, because we know that some surgical tools not only need movement, they also need to perform some grasping of the tissue. And this is done by one of my master students to develop a grasping interface, not affect the movement, and can work together with the motion interface. So we start with 6 foot, actually toe gestures. This is from literature, how what kind of movement the toe can perform. And based on this foot gesture laboratory, we conduct a questionnaire survey with 35 participants. So we ask them to perform this kind of 6 gestures, and they mark what's the difficulty they feel to perform those kind of gestures. And through the analysis of the questionnaire, we found that 2 gestures, that's the toe abduction and foot curl, these 2 gestures are very difficult to achieve for most of the participants. So we remove these 2 gestures. And based on another 4 gestures, so we develop another 3 interface to collect the information of the other 4 gestures. And then we conduct another independency study that to check, so when the toe perform these 4 gestures, what's the movement signals, what's the movement noise, and also when the foot is moving using our proposed interface of motions, so what's the noise of the foot gestures for grasping. Then we found that finally, we found this toe extension and toe flexion have less effect on foot motions than the big toe pressing and the first metatarsal pressing. And then we can conduct another evaluation studies to with a simulator of the laparoscopic surgical tool to ask the user to move a ball and also keep the force, keep the shape of the ball at the same time. And after the 3rd experiment evaluation, we found the toe extension is the best gesture, and most participants prefer this gesture and interface to control the grasping degree freedom. So that's about the foot interface development. And in the next stage, we try to evaluate these hand-free interfaces in a systematic way. So we have performed several experiments to evaluate the 3rd hand control and also the 3 hand control. So we compare the foot interface with the natural hand operation. And we also compare the foot interface with the other 3rd hand interfaces. And in the 3 hand control, we compare foot hand Trimanual control with the sequential bimanual control. And we also perform a study to study why this foot hand, whether this foot hand Trimanual study is better than the human-human cooperation in the normal cases. So the first experiment is evaluating the foot interface with a conventional button tap interface. So we have built a teleoperation system with an industrial robot, and we ask the user to use both foot interface and button interface to control the robot remotely. And the button interface is built based on the conventional button interface used in robotic surgery and in the literature. So they are actually a planar platform with 8 foot switches located on this planar base. Pressing 1 foot switch activate a constant speed movement in the related Cartesian direction. So this is a demonstration of how the experiment is conducted. So we have built a task platform similar as the laparoscopic training. So in this task, the participants were asked to perform to move these robot tools to press the LED button accurately. The LED button is very small. And in the second task is a path following task. So the participants need to use the foot interface to control the tool to follow the defined path without touching the wear. So we have found that the proposed foot pedal interface can work very well, especially in the second task, because it can move naturally in the curved path. For example, diagonal or curved direction, he can just move in that specific direction, which is more intuitive for the user. So the result of this comparison show that the developed pedal interface is 60% smoother than the button interface and also 30% faster. And the pedal interface is also more intuitive and comfortable through the result of the questionnaire. So we have known that the pedal interface is working with the industrial robot, but we still don't know whether it can be used to control a medical tool and how it can compare with the hand manipulation, natural hand operation. And here we perform another study to check whether the foot interface can be used to control a flexible endoscope. And to achieve this study, we develop a foot-controlled robotic endoscope. So in the system, the user can use the foot interface to remote control an endoscope in 4-degree freedom through the vision feedback of the endoscope camera. So we recruit another 10 participants, and we compared foot teleoperation with the hand teleoperation and the direct manual control. So direct manual control is a conventional approach in the practice to manipulate the endoscope to perform diagnose or surgery in hospitals. And hand teleoperation is a common way in robotic systems to operate surgical tools. So we compare these two kinds of hand operation with the foot teleoperation. So we ask the user to use this 3 kind of control way to navigate to 5 targets. And after they complete the targets, we will record the completion time using 3 different kinds of control modes. And the result is showing here. We can see that both the hand and foot teleoperation are more efficient than the conventional direct manual control. And the average response of participants to the questionnaire also showed that the foot teleoperation was felt more comfortable and less fatigue than the direct manual control. But in all these 3 control ways, the hand teleoperation still win. Hand teleoperation is the fastest among all these control ways. But we know that if we use the hand teleoperation, so we can't control all the 3 instruments at the same time. Then in the next study, we perform a 3-hand manipulation study with a 3-limb teleoperative robotic system for endoscopic surgery. So the whole system provides 1 surgeon to control 13-degree freedom of 3 surgical instruments. So in the system, we use 3 interfaces. There are 2 hand interface and 1 foot interface. So the user will need to use the foot to control the flexible endoscope, which is showing the black color, and use the left hand to control the 4th dimension interface to control the left grasper, robotic grasper, and right hand to control the categorizing hook. So we compare this foot-hand manual control with the conventional clutch-based bimanual control. So in many robotic systems, you may find some clutch buttons or clutch pedals to swap between different instruments. So in this case, we add 2 buttons on the hand controller, so user can choose which tool they control in the sequential hand clutch-based control. So we compare this conventional sequential control with the proposed foot hand control. So this is a demonstration of the ex vivo surgical test we have performed. So we marked the foot target on the porcine tissue, and the foot target including 2 exposed target and 2 cover target. For the exposed target, the user need to control their foot to move the endoscope to the proper position and use a cauterizing hook to cut the tissue. And for the cover target, the user need to coordinate all the 3 limbs. The foot need to control the endoscope to the target area to provide proper view. And the left hand will lift the tissue, and right hand need to cutting inside the target zones. The result of this test is showing here, which has verified our assumption that the 3-hand control is efficient than the bimanual sequential control. And the operation time was reduced in average about 44% using the 3-hand control compared to the clutch-based bimanual control. And 3-hand control is also preferred by the participants with less mental effort. But we know that in many other cases, the human is collaborating with their partners. Then whether it's possible that we perform some study to evaluate 3-hand operations compared with 2 human-human collaboration. So before that, I would like to introduce a classification of the 3-hand tasks. So we follow this form. So we want to systematically study different kinds of 3-hand tasks. As shown in the previous slides, we know that there are many different kinds of 3-hand tasks, and the performance of this Trimanual control may also affected by the task type. So we try to categorize all those tasks by checking the coupling of hands and task goals. So this table is trying to separate different kinds of tasks. For example, for the 3 goal all and coupled tasks, coupled here means physical connection of all the 3 hands. So this means if in the simple case means multiple objects pick and place. So each hand will have different goals and they are not coupled together to reach different goals. Similar as the task here. So 3 different hands have different targets and not coupled together. Another case, for example, like 2 coupled, 2 goals, it means 2 hands are physically coupled together and there are 2 tasks they need to achieve. For example, in this case, these 2 hands are coupled together. They need to use the center of mass to reach the target, and another hand have an independent task. For another case, like 3 coupled, 1 goal, it means all 3 hands are coupled together physically, and they also need to reach 1 task. So follow this category. So we want to check, is this solo control really better than direct control in some task? So to achieve that, we need to check first, the augmentation with the supernumerary robotic limb should enable 1 user to complete tasks that require more than 2 hands successfully, which we have checked that. And we also need to prove they can do so with similar or superior performance as through the collaboration with a human partner. So therefore, we evaluate Trimanual coordination under solo and direct mode. But at the initial test, we found that the user still prefer the collaboration with partner because the task is very simple. they feel it's easier to collaborate with a partner. Then in this study, this is already the second study, actually. So based on the previous readout, we try to provide more learning time to the operators because the Trimanual control is kind of a different control way from their daily lives. They don't use it. So we try to, if we see the protocol of the experiment, we provide 4 training sessions to the solo operation. So this is a 3-day study that the performance was initially tested on day 1 for both solo and diet control modes, and followed by 4 training sessions of the solo modes across 3 days. And then after training, an additional test was conducted, and then we compare the final solo and diet performance. So these slides show the learning effect after training. T1 to T4 means 4 training sessions. We can see that there's a clear performance improvement for the solo operation over training sessions, especially for training session 1 and 2. And this slide is showing the initial training at day 1, initial test at day 1 and the final test at day 3. We can see that after 4 sessions training across 3 days, the participants increase the task performance, and all perceptions and performance measures become similar between the diet and solo configurations. So we can see that it's actually can achieve the same level used very short time of training. There are also other demonstrations we have performed with the robotic systems. First one is we collaborate with Sorbonne universities to control a supernumerary robotic limb to collaborate with the natural limbs in 3 coupled cases, but the coupling stiffness are changing in different cases. And the second case, we try to control the orientation of the 2 robotic arms, how they grasping the object at the same time to control the movement using the hand controller. And the third case is about a demonstration using the DaVinci systems. We are using foot to control one of the patient side manipulator and another hand to control another 2 manipulators to perform a 3-2 demonstration. I would like to share some other works from my students on their master projects. So except the body interface, we also developed some robotic assistant for microsurgery. So this is a work of 2 master students to develop a modular robotic gripper for microsurgery, so they can adapt to different instruments quickly. And even the naive user can quickly change the tools, and it will also automatically check the force with the force sensors at the end of the gripper. Another work is about the trimanipulation study with a VR headset. So previous study is on 2D. So this is a study we increased to 3-dimension task. So the student has performed 2 tasks. One is 3 goals task. Another is 1 goal, but 3 dependent tasks. And then they check, the student check whether this training of both tasks can transfer to another hybrid 2 coupled task. So through the study, they found that both kind of training can transfer the learning to the new 2 coupled task. There are also another student, very interesting work on checking the performance, checking the appearance of the supernumerary limb. So whether a human-like appearance or robot-like appearance may affect the performance of the tree manipulations And the results show that the performance are similar, but it's interesting to see that most of the participants prefer the robotic appearance. So we have this study. It's merely we want to check whether the uncanny valley effect may be shown here, but they still need further study to check whether the appearance has some different effects on the tree manipulations. We also have another work on the automatic vehicles, on the haptic feedback of front vehicle motions, of the haptic feedback between the two vehicles. So we try to provide some haptic feedback to so there are two cars. The front car is an autonomous driving car, and the rear car is a human driven car. But we know that the different cars may provide different informations, especially when some obstacles are in the front. So we provide a haptic feedback. There's a haptic communication between these two cars. So we check different stiffness and also the driving with different speed. And the results show that the front vehicle motion can enhance the driving control, reducing the motion jerk and road deviations, also lower the mental effort. So we're suggesting that the haptic communication between these two neighboring cars can be a way to improve the safety and efficiency in automated driving systems. But this is also in the starting stage. Some ongoing projects I now have, we continue to develop some body interface, including the foot interface and finger interface, and also scan interface with the collaboration with University of Tokyo, with some surface EMG interface may be possible to be used for human augmentation. We also have some project working on dexterous and modular robotic anti-effector for the nuclear teleoperation to protect the human from the hazardous environment and also provide dexterous manipulation. And we're also interested in robotic surgery for macro robotic system for macro surgeries. And except this, I would like to share some planned project. If you are interested, I'm very welcome to further discuss any collaborations. So except the human augmentation with intuitive body interface, to further bridging the gap between the third hand control and natural hand control. I'm also interested in human behavior and sensing to study human body redundancy using variable sensings. So we want to check whether there are some regular and augmentation patterns for human with the help of variable robotic system. And we also want to check this kind of augmentation behavior. What's the effect of this kind of augmentation behavior on human, not only on their behavior, maybe on their brain, on their neural systems, and also how to train and how to enable the user to be trained and learn this kind of augmentation. And through our test result, we found that although we provide some hand-free interface to enable user to control the third tool, this actually introduces additional mental and physical load. Some users don't like it. They still want to collaborate with other persons. But in that way, we are thinking that whether it's possible we provide a robotic partner to let the robotic partner to do part of the work through prediction of the human intention and also monitor the human fatigue status. And this may need a task or time-based dynamic shared control between human and robot, and also how robots can learn from human expert to perform the automation tasks. Okay. So this is my last slide. I'm currently also part of the Center for Robotics and Sensing Technologies. So we are new centers, except the medical robotics. We are also interested in unmanned vehicles and automations. high precision robotics and soft robotics. So if you're interested in any collaborations, please feel free to contact us. Okay, so that's the end of my presentation. Thank you very much for listening.
Yeah, we have time for questions if you just want to take questions directly.
Yes, please.
Thanks for a really interesting talk. So it looks like you may be looking into this in the planned work, but so it takes about 2 or 3 days, I guess, for the human training from simple tasks. But then I guess it's not like a sensation that comes naturally with what you're doing with the foot. Have you considered, so for example, with military tanks, they started to design the control systems similar to like Xbox controllers, because I guess the demographic is young boys who got used to playing like violent video games who then start controlling tanks. And the thing is, it saves a lot of training time, I guess, because it's this feeling that comes natural that they've got this brain training. And is that something that I guess you would consider looking into, or have plans to look into, about trying to change the device design so it kind of fits more of a natural movement?
Yeah, that's kind of a research direction we want to continue. We want to make the interface more user-centered. That's why actually we try to get some more feedbacks before our design, and to check what's the intuitive way, what's the fastest way they can control this kind of device. And so some of the, maybe you can see the second design of the grasping interface. Actually, we learned from the previous experience. We try to ask users to choose what kind of gestures they like, what kind of gesture they think are most easiest one they can perform. And then we conduct the experiment step by step. By designing that small interface, we actually perform 3 experiments with the human participants, with more than 50 participants involved in that case.
Will performance degradation of the medical expert there will be used in another study? Like they sometimes have surgeries for 4 hours, 5 hours, and maybe having food may degrade the performance of them making the surgery in the future.
Could I, so you're asking that for the long time operation?
Yeah.
So the foot manipulation.
Having an extra limb to be used, will it degrade? Is it studied or will be studied?
Extra degree of freedom.
Yeah. Extra having an extra limb to be used. Normally they use their hands, now they're also using their foot. Will it degrade the performance at the long run, rather than this normal test?
And the extra load doesn't make them
tired.
Yeah,
right? So,
yeah.
So we try to choose a source independent of hand operations. But as you said, if the human operating in a very long time, they introduce fatigue. In that case, actually, even without foot control, they're doing very long time operations with fatigue. This may still introduce some errors. But the thing I think you want to ask is, once the foot is involved, this actually introduce more additional fatigue to the users. That's one problem. That's also actually design interface. We try to make the foot stay on the ground, so without lifting it. We actually have also many bearings, also many mechanisms inside to reduce the tension. So actually it's a quite smooth move on the ground. And for the foot control tool, it's not like the hand control tool, they need to operate all the time. It's actually operating to the target area, then the foot can rest there. And next time when they need to operate, they will move to another place. So there's some resting time in between. But as you said, if the foot is used to control some continuous manipulating tools, I think that will be introduced along with fatigue.
You see how you were talking about the grasping technique, where you take the object in the robot's grasp. Are you using similar techniques with the hands? Like, is the motion that the hand does inside the robotic a grasp, or is it more of like, is it a different motion that the surgeon has to learn?
It's the same.
Yeah, so it goes, so the doctor goes like that and the hand goes like that. Okay, yeah. I was hoping it was like that.
You had some plots where you were comparing performance before after some tests, and there was a spread, and I reckon that the spread for different surgeons, right? That you, all those dots. You could show maybe one of those plots.
To
Yes, those just something like this, right? Can I ask first of all, are all the various dots for any particular entry, say one or two solo, for different surgeons?
yeah, the dots are for different participants. Yeah.
Yeah, well, let's say surgery in medical.
Yeah.
So it's a bit difficult to see from that because they're all in the same color. But I think it would be interesting to see whether for one specific participant, you see more of an improvement than for other participants, because it seems to me that one goal would be to, because some of them will be at the top, and the relative change in performance won't be quite as significant as essentially making better someone who's already at 40% success rate. You see what I mean? Like if these were surgeons and I had to have an operation, I would want to be overrated on by the people who have success rate of 80%, right?
Yeah, thank you.
And if they go from 80% to 82, that's great, but it would be a lot better to have people who are performing at 40% to get up to 70%. Do you see what I mean? Like,
Yeah. I see for the individual improvement.
yeah, that would be, I think, interesting to present. Maybe you have those details separately. I'd be interested to hear it. But I think it would be nice to know whether individual by individual, your third tool is improving the performance of some of the low scoring individuals to start with.
Yeah, thank you very much. That's a very good point. Actually, we also found that different individuals perform slightly different in our test. So thank you. That's a very good point. We'll continue analyze in individual perspective.
So you are getting 4 degrees of freedom.
Yeah.
Using 4 degrees of freedom on the right leg to control this third hand.
Yeah.
So but you're missing out a limb. Why don't you use the other leg and you have 2 degrees of freedom on each leg to control this third hand? Because it seems like 4 is quite a lot to ask. And I guess if you're trying to implement those 4 degrees of freedom, you're probably not going to stop using your hands. You're going to develop more attention to not using our feet in that way. Whereas if it was just 2 more simple movements on each limb.
Yeah, consider that at the beginning. But in the operation room, actually there are also other pedals. They need to activate the cutting of the carrying hook. There are other pedals they need to press to activate the cutting. So they have another leg is used to press the other pedal.
And there's no, I guess that's the second person. Yeah.
Okay.
Well, yeah, thank you very much.
Thank
you.